In this video, we will look at activity 3D, which is on writing dissociation equations. And so we just need to write the dissociation equation and use the correct type of arrow. And so just to recap, if a compound is very soluble in water, we use a single-sided arrow to show that the compound will remain dissolved. But if something is mostly insoluble, it doesn't dissolve very well in water, we use a double-headed arrow to show that the compound is in the state of trying to be dissolved but mostly remaining undissolved. And so we use two kinds of arrows in dissociation equations to show how much of something is actually dissociated and broken up when it dissolves in water. And so let's look at the first one. The first one is sodium acetate. So we first need to figure out what sodium acetate looks like. To crisscross, we're going to have sodium, which has a +1 charge, and then acetate, which is C2H3O2 with a -1 charge. And so when we crisscross that, we just get Na and then C2H3O2. And then we need to determine what kind of arrow to use. So looking at our solubility rules, I see sodium up here in the first solubility rule, and this compound will generally dissolve in water. There are no exceptions. So this is going to be something that's highly soluble, so I will use a single-sided arrow pointing just one direction. And so sodium acetate is just going to break up into its ion components. So it's going to break up into sodium with a +1 charge, and then acetate with a -1 charge. And this equation already came out balanced because for every one sodium ion in our compound, we have one acetate ion in our compound. And so that's all we have to do. The next one says ammonium sulfate. So ammonium is NH4 with a +1 charge, and then sulfate is SO4 with a 2- charge. So when we crisscross, we get NH4, and we're going to end up getting 2 of those. So I'm going to put this in parentheses, and then we'll end up with just 1 SO4. So NH4SO4, let's determine if that is soluble. So looking at our rules, I see NH4 up here in this first rule, and it says that this compound does dissolve. There are no exceptions, so we know this will fully dissolve, so we're going to put a single-sided arrow here. And then when this breaks up, it's going to break up into NH4 with a +1 charge and SO4 with a 2- charge. But we need to balance this equation because we have 2 ammonium ions for every 1 sulfate ion that we have. So we need to show that on the product side by changing our coefficients. So in front of NH4, I'm going to put a 2 to balance NH4 out. And then sulfate is already balanced with 1 SO4 on each side. Next we have calcium carbonate. We have calcium, which has a +2 charge, carbonate, CO3, with a 2- charge. So when we crisscross, we're just going to get 1 of each, Ca, CO3, because we know we would end up with Ca2, CO3, 2, but then the 2's would cancel out. Now we need to look to see if calcium carbonate dissolves. So I don't see calcium up here. The first time I see it is down here. And it's under the compounds that generally do not dissolve. And carbonates generally don't dissolve. And we'll look and see if calcium is on the list of exceptions. It is not. Calcium carbonate will not be very soluble, so we're going to use a double-headed arrow here. So when this does break up, if it were to break up, we'd get a calcium with a 2+ charge, and we'd get a carbonate with a 2- charge. And this equation already came out balanced. And then last but not least, let's look at potassium carbonate. So potassium has a +1 charge, carbonate, CO3, has a 2- charge. So when we crisscross, we get K2CO3. And then we need to determine if this is soluble. So generally, carbonates do not dissolve. But let's see if potassium's on the list of exceptions. Potassium is on the list of exceptions, so potassium carbonate will dissolve, so we'll use a single-sided arrow. So we have potassium with a +1 charge, and then carbonate with a 2- charge. And then this equation needs to be balanced because for every 1 mole of potassium carbonate that breaks up, we will get 2 potassiums and 1 carbonate. Next we have lead 2 phosphate. So we need to first crisscross this. So we have lead, or Pb, and this 2 indicates that it has a +2 charge. And then we have phosphate, which is PO4 with a 3- charge. So when we crisscross here, we get PB3, and then we're going to end up with 2 PO4s, PO4, 2. And so next we need to determine, is this going to dissociate well, or are we going to use a double-sided arrow? So looking at our list, I don't see lead anywhere on here, but I do see PO4 under compounds that generally do not dissolve, and lead is not on the list of exceptions. So this is not going to dissolve very well, so we're going to use a double-sided arrow here. It will, if it did dissolve, it would break up into lead with a +2 charge, and then PO4 with a 3- charge. And of course we need to balance this equation because in every molecule of lead 2 phosphate we're going to end up with 3 lead ions, and we're going to end up with 2 phosphate ions. We'll put a 3 and a 2 there to balance our equation. Number 6 is barium hydroxide. So barium has a +2 charge, hydroxide is OH with a -1 charge. And so when we crisscross, we get Ba1, and then we're going to get OH, and then 2 of those. So now we need to determine if this is going to dissolve. Looking at compounds of hydroxide, typically do not dissolve, but barium is on the list of exceptions here, so this does dissolve. So we're going to use a single-sided arrow, and we're going to get 1 barium, the 2+ charge, and then we're going to get OH with a -1 charge, but we're going to end up with 2 of those when we balance our equation. Next we have sulfuric acid. Remember, acids always are hydrogen crossed with something else, so H+. Sulfuric acid, there's no hydro prefix, so I know that it's going to be a polyatomic ion, and because it ends in ic, I know it's the polyatomic ion that ends in 8. So this must be sulfate, SO4 with a 2- charge. When I crisscross H+ with SO4 2-, we get H2SO4. Now, I don't really need to look at my solubility rules for this one because this is an acid, and I know that acids must be dissolved in water. So I'm going to use a single-sided arrow for this. H2SO4 is a strong acid. It is going to almost fully dissociate and form H+, and SO4 2-. And then we need to balance our equation. For every molecule of sulfuric acid, we're going to get 2 hydrogen ions and 1 sulfate ion. And this will become more and more important as you go into the portion of this unit on acids and bases. But acids, especially strong acids, fully dissociate when they're placed in water. Then finally, we're going to do the dissociation equation for water itself. And so we have HOH, and I'm going to write it as its 2 ions, so it's really easy to look at how it dissociates. And so HOH is going to break apart into H+ and OH-. And I used a double-sided arrow, or a single-sided arrow here, but really this should be a double-sided arrow because this is constantly happening in both directions. Water breaks apart into its ions and then rebonds with something else as a new ion. So I'll put a double-sided arrow there as well.